So now if we put everything that we've had for curve sketching all together, we've done first derivative test, second derivative test, we've got inflection points, stationary points. How can we put all of this stuff together succinctly so that we have a way of graphing any function and have sort of a system of doing it that works well? So a couple of things when you're sketching. First of all, see if you can find any intercepts, x-intercepts and y-intercepts. Perhaps you can find them without your calculator. Sometimes you can only solve them with your calculator. But those are going to be key points to label on your graph. Also, you're going to look if your function has any asymptotes. So maybe you have some non-permissible values for x that cause you to have some vertical asymptotes. Or maybe as the values of x get larger and larger and larger, you realize that you're going to have a horizontal asymptote for the graph. So we're going to look at x-intercepts, y-intercepts, and asymptotes as sort of general features of our graph before we go into the derivatives. Then you can go into your first derivative and your second derivative. You can find your stationary points, local mins and local maximums. The way that it's listed here, is this the first derivative test or is this the second derivative test? It's the second derivative test because it's using concavity. Okay? Generally speaking, for your local min and local max, you'll probably start by using your first derivative test because you're going to set up your number line. Once you find out where your derivative is equal to 0, you're going to set up your number line to find out where your function's increasing and decreasing, and you'll be able to figure out if they're minimums or maximums or stationary points of inflection from your first derivative test. Then you're also going to look at your second derivative test to figure out its concavity. So you've got where it's increasing, where it's decreasing, if it's positive, love these things, concave up, if it's negative, concave down, easy to remember. And once we have all of that information, then we can sketch our graph. And we can make a really, really accurate graph as a result. Sometimes our graph is going to require us to use our graphing calculator because there's going to be things that we can't solve for. But most of the time we can graph things without our graphing calculator. So if we look at our first example here, and we're about to sketch this, what I like to do as far as organizing my notes is sort of put titles on what I'm solving for. So let's say I start with my x-intercepts and y-intercepts. So I put a little title in my work while I'm writing this out, keeps it nice and organized, tells the person who's marking it, tells myself later when I'm studying it, what was I doing? I'm finding my x-intercepts and y-intercepts. Well, how do I find an x-intercept or y-intercept? You find an x-intercept by plugging in 0 for y. So if I plug in 0 for y, I just need to solve this equation. You can factor out an x, and then the x squared minus 4 factors as a difference of squares. And we get 3 x-intercepts, one at 0, one at 2, one at negative 2. As far as our y-intercept goes, we can plug in 0 for x, and you get 0. But you might have already seen that, because whenever you have an x-intercept of 0, does it make sense that your y-intercept is going to be 0 as well? And so we wouldn't have had to solve that, but it's not bad to show plugging in 0 for x is easy to find the y-intercept. In fact, I'll often find my y-intercept before my x-intercept because I just know it's less work. The easiest thing to do, plug in 0 for x, start off, feel like you've accomplished something, and then you can go from there. So we've already got our x-intercepts. As far as asymptotes go, I can see right away that this one has no non-permissible values. Also, if I look at what happens when x gets really, really big, well, this function gets really, really big because we've got an x cubed. And I know that it'll go off forever. So this one has no asymptotes. I'm not going to write anything down, but I still do that mental check to see if there was that or not. So next thing I'm going to look for are my stationary points. And in my stationary points, I'm going to use my first derivative test. So we set up our equation. Let's find our derivative. F prime of x. Whoa, this is, woo. There we go. It's going to give us 3x squared minus 4. Correct? Yes. So in order to find our stationary points, we set our derivative equal to 0. Move the 4 over, divide by 3. Square root both sides. And we get square root of 4 over 3. You can simplify that if you'd like to. If you rationalize the denominator and square root 4, you'll get 2 root 3 over 3. So we can set up our number line and put negative 2 root 3 over 3 and positive 2 root 3 over 3. And now we need to check values. We need to check values less than negative 2 root 3 over 3, between, and bigger. Now, as far as checking these values, I'm going to have to make some sort of estimation what this is, and then make sure I choose a value that's significantly lower than that. So if I made this square root of 4 is 2, this is about 4/3, somewhere in between negative 1 and negative 2. So if I use negative 10 for that first section, I'll know that that's significantly less. And if we do negative 10 squared, we get 100 times 3 is 300, minus 4 is 296. This section is positive. It's going to be increasing before that. And maybe if you know some stuff about x cubed graphs already from last year, you would have known that as well, even before we started this. Then a value between these two, I would probably choose 0. Plugging in 0 gives me negative 4, so then it's going down. And then choosing a value larger than 2 root 3 over 3, like positive 10, will mean my function is increasing again. So now I know that at negative 2 root 3 over 3, I have a local maximum. And at positive 2 root 3 over 3, I have a local minimum. So since I know that already, I'm going to write my points down. There's my x points. Calculating my y values, I'm going to have to plug that back into my original equation. Plugging those back into my original equation, remember, was not the nicest thing to plug back into, but we can do that. We're going to get negative 2 root 3 over 3 cubed. The negative would be inside. Minus 4 times negative 2 root 3 over 3. Cubing that first function, the negative will still stay negative. 2 cubed will be 8. What happens when you cube root 3? Well, you can see that, just do it off to the side here. You could do root 3 times root 3 times root 3, which would give you square root of 27. And square root of 27 is 9 times 3. So this will be 3 root 3. Or you can imagine it like this. And square root of 3 times square root of 3 will be 3. And you'll get 3 root 3 that way. So depending on how you want to visualize this and do your math, you're going to get 3 root 3 on the top. And on the bottom, when you cube 3, you're going to get 27 minus 8 root 3 over 3. A little bit of simplifying here. So we're going to get negative 8 root 3s over 9 minus 8 root 3s over 3. If I get a common denominator, I'm going to get negative 8 minus 24. Negative 32 root 3s over 9. Oh, that'd be a plus. Thank you. Thank you. So that will actually change that to negative 8 plus 24, 16 root 3s over 9. Not nice numbers, but we were able to calculate that without our calculator. When you wanted to actually plot this on your graph, you still might need your calculator to plug it in. And so this might have been a calculator question just for determining those values. Similarly, we can plug in 2 root 3 over 3. Things are going to be very similar, except this time this is going to be positive, this is going to be negative. So when we're solving this one, you're going to get 8 minus 24. You're going to get negative 16 root 3 over 3. So I'm just going to clear up, as the British would say, my working. And now that I found my 2 points, I'm going to label them. This is my local max. This is my local min. So now I've found my stationary points. The next thing I'm going to look at is concavity. So my second derivative, my first derivative was 3x squared minus 4. My second derivative will just be 6x. It's equal to 0 when x is equal to 0. And so when I do my number line with my inflection point and check a value before 0 and after 0, I see that this one's going to be negative, this one's going to be positive. So here we got concave down, and here we got concave up. I could have also used the second derivative here to say to myself and just check using the second derivative test, is the negative 2 root 3 over 3 supposed to be a maximum? Yes, because this is concave down. That would make it, if there was a stationary point in that section, it would make it a maximum. And same thing with 2 root 3. It's in this section, 2 root 3 over 3, making it have to be a minimum. So you notice that when you're actually curve sketching, because your first derivative test where it's increasing, decreasing, naturally shows you which are maximums and minimums, you rarely use the second derivative test because you don't need to because it's already done. But it's not bad to see that and use your second derivative as a check were my local mins and maxes correct? Were they at the right places? Do they make sense that I made them mins and maxes? And since we already know that the point is 0, 0, because we did that earlier, we can just label that now as our inflection point. Now that we've gone through all of our stuff and we have our points, it's just a matter of putting them on our graph. and setting some sort of scale up. We had 0, 0. I'm going to label my other x-intercepts at 2, 0 and negative 2, 0. We estimated 2 root 3 over 3 to be somewhere, well, we should figure out exactly what 2 root 3 over 3 is with our calculator. We estimated it around negative 1. .15, so somewhere between negative 1 and negative 2. Negative 1.15. I'm just going to go down to these points. And write them in so we have an idea of where they're at. And 3.08. And so now we have all of our points labeled. We have our maximums and our minimums. We have our x-intercepts, and we have our inflection point, which also was an x-intercept from before. Now we can graph our curve. I like to, when graphing a curve, I like to start from my inflection point, because then I can make sure that my concavity is that way, and then that way after that. But it's not hard to start from the left and draw one smooth curve through all the points. Put arrowheads on the end of the graph, and we have clearly sketched our graph of x cubed minus 4x. So here's one for you to try. And I'll put up the final graph, so as you're going along and you're going through the steps, if you've got your x-intercepts and you want to check them, they're labeled there, and you go, ooh, mine are off, so you don't keep going with a mistake. Same thing, you can see where the max and min, they're nicer points than our last graph. We also have 3 inflection points on this one, so you can check those as you go along, but try to set up your work so that it's clear you're doing one thing at a time, you're labeling things well, you're making it nice and neat. So here is the graph of the rational function. Notice this one's going to have some asymptotes. So you're going to have to think, how would I show my work to show that those 2 asymptotes are there? Here, I'll just show this much so you can see that that asymptote's at y equals 1.5. And here's our exponential graph. And the hard part on this one is it does have an asymptote at y equals 0 on the left part. That is something that you most likely would only see if you looked at your graphing calculator. You wouldn't be able to really understand it other than the fact that at a certain point you know that your function will always be negative and it's always increasing. So the only way that that can happen is if it's approaching y equals 0. But we'll talk about that little asymptote when we go over that on the next day. But the other parts of this, your inflection points and your minimums, you can see by the points that are listed there that they kind of imply that in order to graph them, you need your graphing calculator. So that too would help you realize the shape of this graph and what it looks like. Exponential graphs, when they appear on the exam, they tend more often to give you a range which you have to graph within. So you have to graph from -3 to 5. And so when you're graphing a certain range, then you would need to label those endpoints, and then issues like that asymptote on the left wouldn't appear because they would give you a certain range where you had to graph it. And so you would know where the endpoints of your graph would be.